Here, because of that wobbling that goes on, we lose a lot of energy. Now, we can still make some assumptions. If most of the energy is conserved, I could use energy to figure out how fast the ball is going at the lowest point of its swing. Remember, that was one of the questions that was asked during the video? How fast is it going at the lowest point in the swing? Answer this question. The acceleration of the bowling ball of death is constant as it swings back and forth. True or false? True or false? Okay. What I should have asked is it false or way false? Way false. You had a homework problem where you had a bowling ball of death, but actually it was a kid on a tire swing. But if it were a bowling ball of death, it would have been the same problem. We found that acceleration vector changed its magnitude, how big it is, and also its direction. Here, the bowling ball is speeding up and changing direction, turning. Here, it's slowing down and turning. Here, it's just turning. Here, it's just speeding up. Here, it's just slowing down. Now, why is that important? Because the old style approach to these problems relied on the kinematic equations on page 21 of your textbook. But if you look at those four equations on page 21, there's great big yellow caution tape around them. Danger, danger. Don't even think of using these equations unless what? Unless acceleration is constant. And so there are some problems that you can solve both ways. They will be easier with the energy approach. But there are other problems like this one here. If I were to ask you how fast is the ball going at the bottom of the swing, that would be trivial using energy. You would not be allowed to use the kinematic equations. They are not valid because the acceleration is not constant. Let's look at this problem, one of your homework problems, problem 4. In this problem, we have a gymnast that is doing one of these grand loop-de-loops. And as he goes around, he pauses at the top for dramatic effect and then comes zipping down, and we want to know how fast he's going when he gets to the bottom. Now, the first question we ask is, can we use those kinematic equations on page 21? No or heck no? Heck no. The acceleration's not constant at all. So we have to use energy. And in this case, we're going to assume that energy is conserved. Now, what goes into that assumption? Well, where might energy be lost in this system? Friction with the hand. So one way we could get rid of that friction is we could put that white powder on the baby powder on his hand. And then we have to assume that this gymnast has a very, very strong grip. Because you imagine doing a loopy-loop like that with baby powder on your hand. I know that I'd just end up falling on the ground. So he's got to be able to hold that position really hard. And air resistance. We're going to have to ignore air resistance as well. But if we do that, we can solve this problem. If we assume that the energy lost in the friction or through the air resistance is small, then we can solve this problem. Now, the initial energy is gravitational. He's not moving up there, so it's not kinetic. Now, what is the height? Well, that depends on our coordinate system. Now typically we choose the lowest point in the problem as our zero in height. But when you're dealing with a human, well, my head's at a different height than my feet. I'm messy. And so what we're going to do is we're going to model that human. We're going to find later in a tutorial that we can do this. We're going to model the human as if all of the mass is located right at the center of mass. And the center of mass for a human your age is about 2 inches behind your belly button. For a human my age, it's about 8 or 10 inches behind the belly button. You'll get there. Don't worry. Okay? So what we're going to do is we're going to choose our zero of height at the location of his belly button when he's at the lowest position. Now we're told that the distance between his belly button and his hand outstretched is 0.9 meters. And that means his initial position for his center of mass, his belly button, is 1.8 meters above our zero. Now, when he gets down here, because of my choice of zero height, he has no potential energy there. He has only kinetic energy. Now, you'll notice in this problem, if you've read it, that we don't give the mass of the gymnast. And this frustrates some people. Well, how do I find the kinetic energy without the mass? How do I find the potential energy without the mass? Well, the key is, when I set those two equal to each other, both sides have mass in them, and I can cancel out the mass. That is the most important principle at Disney World. Okay? When you have a roller coaster where all the energy is either gravitational or kinetic, that mass is going to cancel out. What that means is that everyone's going to get to the end of the ride at the same time. That's important. You don't want to leave the heavy guys behind. We all get down to the bottom of the roller coaster together because the mass cancels out. So now it just becomes plug and chug. Now, folks, this next exam that involves energy is one in which I have typically every semester lots of high scores and lots of very low scores. And I wish I could say it was people that understand energy and those that don't understand energy, but that's not what it is. What it turns out to be is those that can do algebra and those that can't do algebra. It turns out that when you do energy problems, they very quickly turn into an algebra problem with one unknown. And you just solve for that unknown. That's why it's not my favorite thing to teach. It's like teaching math, and who would choose that voluntarily? That's silly. Okay? I hope I haven't offended anyone. But what I'm saying is that if algebra in particular is not your strong suit, it is time to practice. It is time to brush up on those skills, because that's what you will be doing on that third midterm. A lot of algebra. Okay? Now, folks, we still have 5 minutes left, but unfortunately we've run out of lectures. So I'll let you go early. We'll give you a rebate in the mail. Check your mail. It'll be coming.